The Mesozoic Era, spanning approximately 180 million years, was a time of extraordinary biodiversity and the age of the dinosaurs. This era, divided into the Triassic, Jurassic, and Cretaceous periods, provided ideal conditions for the evolution of gigantism in dinosaurs. Key factors such as an abundant food supply and a favorable climate played pivotal roles in enabling dinosaurs to grow to massive sizes. Abundant food supply, a herbivore's paradise. The Mesozoic era saw a remarkable flourishing of plant life, driven by high levels of carbon dioxide and warm temperatures. Dense forests of cycads, ferns, ginkgos, conifers, and later flowering plants, angiosperms, provided a steady and abundant food source for herbivorous dinosaurs. The massive size of herbivores like Brachiosaurus and Diplodocus can be attributed to this plentiful vegetation. As herbivores grew larger to take full advantage of the abundant food supply, they inadvertently triggered an evolutionary arms race. Carnivorous dinosaurs such as Allosaurus and Tyrannosaurus rex had to evolve larger and stronger bodies to hunt and prey on these massive plant eaters. This dynamic pushed both herbivorous and carnivorous species to unprecedented sizes, creating a feedback loop of evolutionary gigantism. Favorable climate, nature's greenhouse. The warm and stable climate of the Mesozoic era further supported the evolution of gigantic dinosaurs. Global temperatures were higher than today, with minimal polar ice and widespread tropical and subtropical conditions. These factors contributed to 1. Enhanced plant growth. The greenhouse effect, driven by high atmospheric CO2 levels, created conditions ideal for lush vegetation. The resulting food surplus supported the energy demands of massive herbivores and their predators. 2. Boosted growth and metabolism. Warm climates likely accelerated the growth rates of dinosaurs. Evidence from bone histology suggests that some dinosaurs, such as sauropods, experienced rapid growth during their early years, reaching gigantic sizes relatively quickly. The consistent warmth may have also allowed dinosaurs to maintain relatively high metabolisms. While debates about whether dinosaurs were warm-blooded or cold-blooded continue, their ability to grow large and thrive in diverse environments reflects adaptations that likely leveraged the favorable Mesozoic climate. A perfect evolutionary storm. The combination of an abundant food supply and a greenhouse-like climate created a perfect storm for evolutionary gigantism. Herbivorous dinosaurs thrived in their roles as primary consumers, while carnivorous dinosaurs evolved to match their size and strength. Together, these factors drove the diversification and dominance of dinosaurs during the Mesozoic era. This era not only highlights the interplay between climate, ecology, and evolution but also underscores the dynamic nature of life on Earth, where environmental conditions shape the path of biological development in profound ways. Physiological factors that helped dinosaurs grow gigantic. The gigantism of dinosaurs during the Mesozoic era was not only a result of external environmental factors but also their unique physiological adaptations. Dinosaurs evolved specialized features that allowed them to grow to massive sizes while maintaining mobility and biological efficiency. Key factors include their efficient respiratory systems and lightweight bone structures, which were integral to supporting their enormous bodies. Efficient respiratory system, powering massive bodies. One of the most remarkable adaptations seen in dinosaurs, particularly in sauropods and theropods, was their highly efficient respiratory system. Many dinosaurs are believed to have had a bird-like respiratory system with air sacs connected to their lungs. These air sacs allowed for unidirectional airflow. Unlike mammals whose lungs process air in two directions, air sacs enabled dinosaurs to extract oxygen more efficiently, as fresh air constantly flowed through their lungs. This was crucial for sustaining their massive bodies, especially in the oxygen-limited Mesozoic atmosphere. Oxygen delivery. The increased oxygen exchange capacity supported the metabolic demands of their enormous muscles and organs, allowing them to grow larger and remain active. The respiratory system's efficiency was comparable to modern birds, making it a vital adaptation for the evolutionary success of large dinosaurs. Lightweight bone structure, a balance of strength and mobility. Another key adaptation that enabled gigantism in dinosaurs was their lightweight yet strong skeletal structure. Many dinosaurs had hollow bones, which reduced their overall body weight without compromising structural integrity. These hollow bones were reinforced with internal struts, similar to the structure of modern bird bones. Advantages of hollow bones included reduced weight. By minimizing skeletal weight, dinosaurs could grow larger without becoming too heavy to move efficiently. This adaptation was particularly important for sauropods, which could reach lengths of over 30 meters. Structural strength. The internal struts within hollow bones provided the necessary support to handle the immense stresses caused by their size and movement. This combination of lightness and strength allowed them to maintain mobility despite their enormous size. A synergistic system for gigantism. The interplay between these physiological adaptations, an efficient respiratory system and a lightweight skeletal structure, allowed dinosaurs to achieve sizes unmatched by any other terrestrial animals. These features enabled growth. The efficient oxygen supply and reduced skeletal weight minimized the metabolic costs of supporting a massive body. Maintain mobility. Despite their size, these adaptations ensured that dinosaurs could move efficiently, whether grazing, hunting, or escaping predators. The physiological innovations of dinosaurs showcased the remarkable evolutionary pathways that enabled their success during the Mesozoic era. By addressing the challenges of gigantism through specialized adaptations, dinosaurs secured their place as some of the most extraordinary creatures in Earth's history. The protective advantage of large size. Gigantic size was not just a byproduct of evolution for dinosaurs. It offered significant advantages in survival, protection, and resource access. Being large provided physical defenses against predators and enabled dinosaurs to exploit resources that smaller species could not reach, reinforcing their dominance in prehistoric ecosystems. Protection from predators. Size is a shield. One of the most apparent advantages of large size was the protection it offered against predators. Massive dinosaurs such as Argentinosaurus and Brachiosaurus were nearly impervious to attacks from even the most formidable carnivores of their time. Predators were less likely to target these giants due to the significant risks involved in hunting them. Deterrence factor. Predators like Allosaurus and Tyrannosaurus rex generally targeted smaller, more vulnerable prey. Attacking a giant herbivore often required a coordinated effort or carried a high risk of injury or death for the predator. Natural armor. In some cases, large dinosaurs also developed additional physical defenses. Smaller dinosaurs, in contrast, relied on agility, speed, or camouflage to evade predators, strategies that were less reliable than the sheer physical dominance of larger species. Larger size allowed for access to more resources. Gigantic size also provided distinct ecological advantages, particularly in accessing food and resources that were unavailable to smaller species. 1. Reaching tall vegetation. Large herbivores such as Brachiosaurus and Diplodocus used their long necks to graze on treetops, accessing food that smaller dinosaurs and ground-dwelling herbivores could not reach. This feeding strategy reduced competition for resources and allowed sauropods to thrive in environments where other herbivores might struggle. 2. Traveling long distances. Large dinosaurs could travel vast distances in search of food or water, an essential adaptation during periods of drought or environmental stress. Their large stride lengths and efficient energy usage allowed them to traverse diverse terrains, ensuring survival in fluctuating climates. 3. Energy efficiency. Larger animals generally have lower metabolic rates per unit of body mass. This meant that gigantic dinosaurs could sustain themselves on relatively less food per kilogram compared to smaller species, further optimizing their resource use. A dual survival strategy. The protective advantage of large size allowed dinosaurs to dominate their ecosystems, reducing vulnerability to predation while maximizing resource access. This dual strategy of defense and ecological exploitation contributed to the evolutionary success and longevity of large dinosaurs throughout the Mesozoic era. The evolutionary push toward gigantism in dinosaurs was not merely a race for size but a practical adaptation to the challenges of predation and resource availability. By growing larger, these prehistoric giants ensured their dominance in the Mesozoic ecosystems, becoming some of the most resilient and successful animals in Earth's history. Comparison with mammals. Why didn't mammals evolve to be as large? Dinosaurs achieved extraordinary sizes unmatched by mammals in terrestrial ecosystems, despite both groups sharing common evolutionary pressures. This discrepancy can be explained by key physiological and reproductive differences between the two groups, which influenced their evolutionary trajectories and size potential. Physiological limitations of mammals. Mammals, unlike dinosaurs, face inherent physiological constraints that limit their growth potential. 1. Live birth and gestation periods. Mammals give birth to live young, which requires their bodies to carry the full weight of their developing offspring throughout gestation. Larger mammals must sustain longer pregnancies and bear significantly larger fetuses, which can strain the mother's physiology. Prolonged gestation periods also reduce reproductive frequency, making it challenging for mammalian populations to sustain themselves if environmental conditions change or predation rates increase. 2. Bone structure. Mammalian bones are generally thicker and denser compared to the lightweight, hollow bones of many dinosaurs. This heavier skeletal structure limits mobility and requires more energy to sustain, making extreme gigantism less feasible. For instance, the largest land mammal known, Paraceratherium, reached about 15 to 20 tons, far smaller than the largest dinosaurs like Argentinosaurus, which could weigh over 70 tons. Mammalian bones simply cannot scale up efficiently without becoming excessively heavy and unwieldy. 3. Thermoregulation. Mammals are warm-blooded and rely on high metabolic rates to maintain constant body temperatures. The energy demands of such a system increase exponentially with size, making it inefficient for mammals to grow to the sizes of the largest dinosaurs, especially in environments with limited resources. Reproductive advantages of dinosaurs. Dinosaurs, in contrast, had reproductive strategies that bypassed many of the size constraints imposed on mammals. 1. Egg-laying as a size enabler. Dinosaurs reproduced by laying eggs, which allowed them to sidestep the physical limitations of carrying live offspring. Eggs, regardless of the parent's size, were relatively small and lightweight, freeing dinosaurs from the physiological strain of prolonged pregnancy. For example, even the massive Argentinosaurus likely laid eggs no larger than a basketball, enabling it to produce multiple offspring in a single reproductive event without compromising its mobility or health. 2. Faster population growth. Egg-laying allowed dinosaurs to produce large clutches, increasing their reproductive output compared to mammals. This high reproductive rate compensated for the risks of predation and environmental challenges, ensuring the survival and proliferation of large species. 3. Development outside the parent's body. Once laid, dinosaur eggs developed independently of the parent, reducing the energy investment required from the mother. This enabled dinosaurs to allocate more energy toward their own growth and survival, facilitating the evolution of gigantism. Additional ecological factors. Beyond physiological and reproductive differences, ecological factors also contributed to the size disparity. Dinosaurs lived in a Mesozoic world with warm climates and high atmospheric CO2 levels, promoting lush vegetation and abundant food sources to support their massive sizes. By the time mammals began to diversify after the dinosaurs' extinction, cooler climates and less stable ecosystems constrained their evolutionary potential for gigantism. A contrast of evolutionary paths. While mammals evolved toward complexity, social structures, and energy-intensive reproductive strategies, dinosaurs leveraged lightweight skeletons, efficient reproduction through eggs, and environmental abundance to dominate terrestrial ecosystems with unprecedented size. These differences highlight the divergent paths of evolution and explain why mammals, despite their success, never rivaled dinosaurs in sheer size. Other potential reasons for dinosaur gigantism. The gigantism of dinosaurs remains one of the most fascinating aspects of their evolution. While physiological and environmental factors played significant roles, other potential reasons for their enormous size include strategies for protection, resource competition, and territorial dominance. Ongoing research continues to shed light on the complexities behind this phenomenon, exploring a variety of interconnected theories. Growth and protection from predators. One of the most practical explanations for dinosaur gigantism is the role of size in defense and survival. Large dinosaurs were less vulnerable to attacks from predators, as their massive size made them formidable and difficult to overpower. Deterrence against predators. Herbivorous giants like Argentinosaurus and Brachiosaurus were virtually immune to predation by most carnivores due to their sheer size. Predators would face immense risks when attacking these massive creatures, as a single defensive movement, such as a kick or tail swing, could inflict fatal injuries. Even apex predators like Tyrannosaurus rex were unlikely to target the largest dinosaurs unless desperate or hunting in groups. Defensive adaptations. Gigantic size often worked in conjunction with other defenses. For instance, Stegosaurus used its spiked tail, and Ankylosaurus relied on its armored body and club-like tail for protection. Sauropods, while lacking direct defensive weapons, relied on their size alone to discourage attacks. By growing larger, dinosaurs not only improved their chances of avoiding predation but also prolonged their lifespan, as adult individuals were often too large to be hunted. Competition for resources. Another potential driver of dinosaur gigantism was competition for food and other resources. As ecosystems evolved, the ability to exploit new food sources and secure territories became crucial for survival. 1. Access to elevated food sources. Large herbivorous dinosaurs such as Brachiosaurus and Diplodocus developed long necks to graze on vegetation high in the treetops, reducing competition with smaller herbivores that fed closer to the ground. By accessing exclusive food sources, these dinosaurs could sustain their massive sizes and avoid direct competition with smaller species. 2. Traveling long distances. Larger dinosaurs had the physical capability to travel great distances in search of food and water. This advantage was particularly important during periods of drought or resource scarcity. Fossilized trackways suggest that sauropods migrated across vast regions, following seasonal vegetation patterns to sustain their enormous appetites. 3. Territorial competition. Size also played a role in territorial dominance. Larger dinosaurs could intimidate or outcompete smaller rivals for access to critical resources like feeding grounds or nesting sites. Carnivorous giants like Tyrannosaurus rex may have used their size to establish dominance over hunting territories, reducing competition from smaller predators. Ongoing exploration, theories and discoveries. Despite significant advancements in paleontology, the exact reasons behind dinosaur gigantism remain a subject of active research and debate. Scientists continue to test and refine theories including thermal regulation. Larger bodies may have helped dinosaurs maintain stable internal temperatures in varying climates. Energy efficiency. Gigantic size may have allowed dinosaurs to store energy more effectively, giving them an advantage during periods of scarcity. Reproductive success. Larger size could have been advantageous in mate selection, with bigger individuals displaying greater strength and fitness. Recent discoveries such as fossilized soft tissues have provided additional insights into the biology and behavior of giant dinosaurs, helping paleontologists uncover new clues about their evolution.